Good morning, YouTubers. So for today's video, we're going to be tackling MIG welding, fillet welds. I haven't really tackled that, and this is one of those that definitely is a very common welding joint, and you're going to do a ton of this when you start building stuff. So that's what we're going to be doing. Let's get into it. So today we're going to focus on doing fillet welds, or T-joints as some people call it. If you call it that, that's fine. I might even call it that occasionally. But your humble fillet weld, very common joint. Pretty much anything you're going to weld, generally speaking, will have some form of a fillet weld. Like if you're going to weld some kind of, I don't know, furniture or something, and you have square tubes, well, you're going to have to do a joint like this commonly. That's a fillet weld, so that's what we're going to be covering. Now, material-wise, if you use 3.2 1/8", that's going to be far easier to learn on than anything thinner. Not to say you couldn't. The reason is that it's harder to burn through, melt through this and make holes. If you were to start with sheet metal, yeah, once you could weld it competently, you'd be pretty good at anything thicker, but your frustration factor is going to be sky high with that, because as you're learning, melting holes isn't any fun because it's extremely difficult to fix that. In the future, I'll teach you how to fill holes and stuff, but for right now, we're going to focus on this. So I would recommend 1/8" material. You can go a little bit thinner. You can go thicker, but keep in mind, like this is 1/4 inch. You're going to be paying a lot of money for this material, double what this is, and to do a couple welds, it's kind of, I don't want to say foolish, but I think you get the point. So stick with something around 1/8, 1/16. Now, these are really easy. When you're learning, it might seem a little bit harder, but it really just comes down to getting your settings even close to what they should be, and then controlling your travel speed. So what I'm going to do is I'm going to tack up all of these, and then we're going to get to welding them, and then I will comment as we go. So to start things off here, we're going to keep it real simple. I'm running 18 volts, 190 inches per minute. My inductance is set for 6. My machine goes to 9. So middle of the road. If your inductance isn't adjustable, then it doesn't matter. We're just going to run a single stringer bead all the way, I don't know, halfway down, stop, look at it. Now this machine's settings chart seems to be actually more accurate than I would have thought it would be, and I'm pretty happy with that. Your machine may not be that accurate, so you're going to have to go by what your machine says in order to determine if you need to adjust anything. But let me run a weld and let's talk about it. All right, if we look at this bead here, we can see that there's a fair amount of spatter down here, which that likely could just be inductance. If I raise my inductance a little bit, the spatter would likely get a little bit better. I am using 035 wire for this as well. I'd probably be better suited for 030. That may help a little bit with that, but I like the look of it overall. It's not bad. Our heat affected zone lines are looking pretty good as well. I don't see, really too many defects here. So we're gonna see if we can't get some of that spatter out of there. So I'm gonna raise the inductance a little bit and see if that makes a difference, but we'll keep the same settings. From a side profile shot, if you look at that, slightly convex or flat, and that's looking pretty good. The weld size is also very appropriate for 1/8" material. So far, all good things other than the spatter. Let me raise the inductance and see what happens. So when we look here, the spatter is significantly less. Most of the spatter you're seeing here is from this weld actually. Now my travel speed slowed down way too much. That's simply because I really couldn't see what I was doing, but the weld itself looks really good, I would say. The heat affected zone, you can see how much different that is. That's a real good indication that our travel speed slowed down, not to mention the weld's wider. When you look at the side profile of it, pretty clean looking weld. I just need to get in a better position to where I can see what I'm doing, and then we will run another one to finish this up and see if I can't dial it in. I also find it interesting, the weld profile smoother than this, which is very common with inductance being raised. So as you can see, just a little bit change in travel speed, clean that right up. So much smaller of a weld. It looks like the bottom toe line's a little bit cold, but it's really just the soot on there. If I wiped it with the wire brush, it would come out a lot cleaner. Now the heat affected zone is still pretty high, and that's partially because we're at the end and partially because this has been heat soaked already. But a slight change in travel speed is all it took to change the weld size, same settings, everything. So that's looking pretty good. I'm gonna let this plate cool off. We're gonna go and do another one, and I'm gonna show far too cold and far too hot, so you have an idea of what those look like, and then we're gonna go to arc footage. So now I have the machine set for 16.5 volts and 130 for the wire feed speed. The settings are roughly equal to, I don't know, far thinner, like under 16th. So what we should see is a humped up bead with poorly wetted in toes, but we'll see what happens. Well, it welded. However, when you look at it, it's got a ropier profile rather than flat. The toes are a little bit cold. Overall, it did do it. However, there's going to be very little penetration if I cut and etch that. So definitely not the most desirable. It did do it though. Now, it's worth mentioning now, since I haven't done a whole lot of talk about this, the short circuit MIG process, short arc MIG, is notorious for making welds that look halfway decent that have no penetration. And just by looking at here, especially the start is really cold. After that, it kind of looks okay. I have a feeling if we cut this open, there'd be virtually no penetration. If I did this over mill scale or rust, this thing, I could probably take a pliers and crack right off because of how little fusion to anything there would be. Now, again, if I were to spray this with a coat of paint that would hide this line down here of lack of fusion, it wouldn't look bad enough for you to second guess that, oh, it's probably a decent weld, but the reality is it's not. And that's one of the reasons why, like on thicker plate, 3/16 and thicker, I'm a huge proponent of flux core wire with a MIG machine or stick welding. The reason is that if the bead looks decent, there's penetration. Like, you can't really have a stick bead stick weld that looks really good that has completely no penetration. It just doesn't happen like it does with MIG. And again, I'm not bashing MIG here. It's just you have to know what you're doing and run hot enough settings to where you actually get fusion. And it's also important to test your welds, because if you don't, how do you know where you're at? You don't. So I'm going to go a little bit colder yet, run a little weld, and then we'll go up in settings. So now I have the machine at 16 volts and 110 inches per minute. This is suitable, I believe it says, for 18 gauge, so nowhere near the thickness this is. I tried to weld with that, and you could just tell by the sound that ain't gonna cut it. And if we look here, see how poorly that's wetted out? I mean, it's a literal bead of caulk on a plate. Not good at all. There's gonna be zero fusion in there at all. You know, if you welded a whole weld like this, you're going to have a failure without a doubt. So completely too cold. Now let's run some settings for 3/16 plate instead of 1/8. So our settings are 20.5 and 290, so massively higher than where we were at. Be interesting to see what happens running too hot. Now, I don't know if you can tell by how red that was, the amount of heat input was pretty high. My travel speed was flying. Now, I was successful in welding that, there's no question about it, and it doesn't even look that bad. But the settings were just simply massively too high. What you're gonna find is, if you have fairly low skill with, or practice really, you're not going to be able to control that like I did. You're just going to melt through because you didn't increase your travel speed. I recognized what was going on, just simply move faster. The interesting thing is, now a lot of this is just from the heat soaking of this plate, but when you look at this, the heat affected zone, and get that in view, there you go, was actually pretty close to what this was until I hit the end. So even though I put more heat in it in the short run, like for this, because I moved so fast, my overall heat input actually wasn't that much higher than what it was here, despite the fact, well, I got better penetration, it wetted out better. Now, due to the amount of wire I was feeding in there, you can see this would be an appropriate weld size for 3/16 material. That's simply too big of a weld for this 1/8 inch material, and we don't need that big of a weld, so that's another downside to moving too fast. If we look on the back side, wowzers, that's hot. No penetration through. Had I slowed down at all with this settings for the 3/16, it would have started melting through on the back. I have no doubt about that. It had enough heat. Again, heat affected zone lines aren't that much different here than they are here. Pretty interesting in that respect. So lack of fusion is really going to be a problem when you're running colder. So I always tell people you're better off running too hot and just moving faster than you are running too cold. Because which weld would you rather have, this one or this? I would take this one, even though it's a little bit oversized. This one will likely fail under stress. All right, let's get some arc footage and talk about what we're seeing there. All right, you can watch this in real time and then I will slow it down. So let's watch the slow-mo now. You can see I started the arc. Everything's looking really good. It's not really that wide. I would say it's an appropriate width for 1/8 inch material. If I was welding quarter and I was this far zoomed in for this video, you would see a wider puddle because I'd be depositing more metal. You can tell that that liquid molten puddle is staying very consistent in size. My travel speed, again, this is slowed down, is staying very stable. This is exactly what you want to see. This produces an ideal weld, and we will see what the actual weld looks like once this is done. So again, real time, and then we'll slow it down. So this is quarter speed, so very slowed down. Same deal as a previous video. Start the arc, my puddle gets to the size that I want, and the size I want is basically determined on how thick a material I'm welding. And then I just slowly push or drag, depending on the piece, the molten puddle. And you can see how consistent this is. Like, you don't see the molten puddle changing shape. You don't see it getting massively wide. You don't see it necking down and disappearing. Everything about this is exactly what you want to see, including you don't see massive pieces of spatter blowing out of it. That's also a telltale sign. And then you can see the finished weld on the picture. Keep in mind that was a little bit more voltage than the first one. We'll leave this one in real time. So right off the bat, you probably noticed it was far, far too fast. Not only was it travel speed far too fast, if you watch how thin that weld is. Now this, if you were welding like, I don't know, 22 gauge might be an acceptable width of a weld, but on this material, to have that thin of a weld or a molten puddle is telling us we're depositing too little metal, so either we need higher settings or we need to slow down. You'll see a couple times where the wire starts stabbing the bare plate because the speed's so high that it essentially lost the molten puddle, like right there. It's a definite telltale sign that you're moving too fast. So we'll watch it real time and I'll comment later. So I'm pretty sure you guys saw that's far too big of a weld. At the start, everything looks good right now, but then that weld pool just keeps growing and growing, and this is simply due to too slow of travel speed. By the time I even got moving, the weld was about twice as wide as it should have been. Now, this is 1/8 inch material. I was able to get away with it. Had I been running hotter settings, I would have blown a hole out the back, or it would have started popping out of that molten puddle a lot worse. Or if I was welding thinner material, I would have just made a hole. So clearly too far, too big of a puddle, too slow. Increase the travel speed or cut back your settings. You know, if you're running far too hot, you can get the same appearance as this, even though you're traveling at a reasonable speed. So that could be an issue as well. But if your settings are close to what your machine recommends, you're probably just traveling too slow. And this is where experience really plays a role. You can run far too hot settings and control it simply by travel speed, but you have to have more skill, more practice under your belt to do it. But this is simply not too high of settings, just too slow of travel speed. All right, so where does that leave us? Well, I think the same way most of my videos, and that's consistency matters. The more consistent you are at your travel speed and your movement, the better your welds. And we saw that I ran too hot, too cold. Generally speaking, too hot is better than too cold, especially if you're welding on 1/8 inch or thicker plate. Too cold is going to be a huge problem. Like, the goal of welding is to have fusion, and too cold means no fusion. It's that simple. Now, realistically, the too hot settings, like some of those over there, made acceptable looking welds. Is just that they're realistically oversized for what we need. You know, putting down a 1/4 inch weld on something that's 1/8 inch is just putting more heat in it than it needs. It's not going to be any stronger with a bigger weld because the weld far exceeds the base metal size. And I thought I would show you here. I have a fillet weld gauge for 1/8 inch material. And if we look here, this would focus for us. That's pretty accurate to 1/8. There you go. Pretty accurate, a little bit over, not too bad. This is the appropriate size weld. And we can also take a look that it's not underfilled, and that does touch the peak of it. So this is about the size weld that you want to be aiming for, somewhere between these two. When you start talking about these, you can see how much bigger this is. I mean, look, that's like acceptable for 1/4 inch plate. Definitely too big. One of the huge detriments in depositing too deep of a weld on MIG with short circuit, like with these guys, as you're just sitting there, just pushing in more and more metal, that arc in the wire is only stabbing at the face of this. So basically like maybe a millimeter or a 32nd of an inch under the surface. So what happens is, as you sit there and funnel that wire and they're just pouring it in there, you're not going to get more penetration in here because all the heat's going to the surface. And that's why you got to be very careful when welding thick plates with MIG. If you're riding that puddle where your wire's just sitting on the top of the puddle rather than closer to the edge, what's going to end up happening is you're just going to stack metal on metal with no penetration. And I'll have a video coming out soon that demonstrates that. And like I said earlier, it'll open your eyes on some things not to do. Now, with that said, fillet welds really aren't that hard, but you guys are going to have to practice. This is probably one of the most useful, if not the most useful joint, so spend your time dialing this in. Yes, it sucks. Yes, it's not building stuff, but when you can get to be decent enough to be running welds like these two, that's a little cold. Or even like this one here is a little better, that's too cold. You get the picture. You'll be much better off, and you'll be able to make some pretty cool stuff. So put it into practice, guys. Until next time, thanks.